Okay, so previously I kind of went over what Rungle Buddy is and what my thoughts were behind designing it, and also what the basic inputs and outputs are, the controls, and the overall functionality is. But everything was conceptual so far, so I'm going to try to get to the fun part now and just show you what Rungle Buddy does by looking at the oscilloscope and listening to it. So generally, Rungle Buddy isn't something that you would listen to on its own. It is more meant for creating signals that are control voltages to modulate other things, but it can certainly make its own sounds because it can actually run fairly fast. But what I want to do partially in this video is, in addition to demonstrating what it does, I'm going to do a little testing of my own and see if we can clock the module and see how fast the internal oscillators go, and also how fast we can run it with a really fast external oscillator. So let's try and do some of that stuff. So let's power them up here. And let's turn on the oscilloscope too. Pardon the noise, this thing is kind of loud. Okay, so this top row here, they're kind of not really centered, but since we're dealing mostly with 0 to positive range voltages, I kind of shifted everything down a little. So where you see those two lines right now is basically that's just 0 volts for signal 1, which is the red, and signal 2, which is the orange. So let's check out the clock that's built in and see what the frequency range is here. So I had mentioned previously that there is some normalization here where the clock, the yellow oscillator, is normal to the clock input and the green oscillator is normal to the data 1 input. And the only way to break that normalization is to plug into those inputs. So these two outputs here are just dedicated outputs, so you always have 2 square oscillators. So I'm going to plug our first channel in to the scope, and you can see it on there. And I'm going to go to measurements. I want to look at the frequency. So let's just turn it all the way down. Looks like we can still see it on the scope here. So it's about almost 600 millihertz, I suppose. So about 0.5 hertz. So that's pretty slow. It's good. Let's turn it up a little and see. So even up about a quarter of the way, we're still less than 1 hertz. Wow, so it actually has to go above halfway just to get to 1 hertz. So I guess this potentiometer maybe is not the right choice, but that's okay. Wow, only 2 hertz at like 3/4 up. Okay, well, that's fine. Generally, I want to be clocking this thing with an external clock, but I put these 2 oscillators on here just to have something to let it work on its own. Let's just keep going, see how clean this thing is at higher frequencies. Hertz. Let's zoom in a little bit here. Now we're at 40, so it's audio range 85. Let's keep zooming in. Oh, we got a little freaky there. Probably my trigger range, but let's see, we're at 124 hertz. Let's turn this up a little bit. Okay, so it kind of starts getting non-squarish at the maximum range, but still fairly clean, and it's about 480 to 485 hertz. That's cool. Let's try the other one. I think this one is actually slower. I used the same capacitors for these two oscillators, but different resistors. So these two oscillators are super basic hex inverter oscillators using a CD40106 hex inverter IC, and there's a very simple oscillator setup you can use that has just a capacitor, a resistor, and a potentiometer, and yeah, that's all this is here. So let's see. Zoom back out here. Gotta go a little further. Oh, a little further still. Let's see. Okay, so the green oscillator, slightly slower, 533 megahertz. Now let's crank this bad boy and see what happens. Okay. Whoa, okay, too much. Alright, so we're already up into audio range, 263. Let's turn the trigger level up a smidge, because this is going to get very sloped, I think. Oh yeah, this thing is, well, that really scrunches down there. So it's pretty fast. It's able to go up to almost 1,000 hertz. So that's cool. So I did a bunch of testing with different components in here to see what kind of ranges I could get out of just having a single potentiometer. And I think that the reason why you lose high frequency is if your capacitor is not small enough, it can't discharge in time, and so that's why you start getting this slopiness here. But if you use a very tiny capacitor, then you're not able to get down into these nice low ranges, and really I wanted something that was potentially quite slow, like something you could just easily watch progress through, and you know, if it goes up into audio range, great. And so I'm satisfied with this here, but certainly you could drive this with much faster or much slower signals. This is just to get you going. So, all right, let's take a little break there.